Nothing really changes when we change the capacitance with the static membrane potential. That's because the capacitance only begins to exert its effects when the membrane voltage changes in time. Decreasing the membrane capacitance made the membrane snappier and more responsive to change. Increasing the membrane capacitance makes the membrane more sluggish. We'll formalize this in a minute, but first, let's explore what actually determines the membrane capacitance. This is a somewhat advanced question requiring some knowledge of physics, so we won't quiz you on it. In a capacitor, an important determinant of capacitance is the nature of the dielectric material sandwiched between the conductors. If we have a material with a higher dielectric constant, which has to do with how easy it is to electrically polarize the material, then the capacitance goes up. If we have a material with a lower dielectric constant, then the capacitance goes down. If we increase the physical separation between the two conductors by making the dielectric thicker, the capacitance goes down. If we make the dielectric thinner, bringing the two conductors closer, then capacitance goes up. If we wanted the membrane to respond more quickly, we'd either need a different dielectric material, or we need to somehow make the membrane thicker. Cells use the fatty lipid bilayer as a dielectric, and it's a pretty good dielectric, all things considered. It turns out that in cases where lowering the membrane capacitance is especially important, nature has come up with a clever solution for creating a thicker membrane. Some axons use a special trick where they effectively wrap more layers of membrane around the axon in a process called myelination. We'll talk more about myelin 2 lessons from now, but for now, it's worth recognizing that nature has tricks for manipulating nearly every electrical property of the membrane when it needs to. Of course, it's worth noting that we don't always want capacitance to be lower. Sometimes we want to integrate signals across time, so it's useful to have a more slowly changing membrane potential that can average signals over time. We'll talk more about this temporal integration of signals in a future lesson when we talk about synapses. Let's see how we can formalize this notion of responsiveness of the membrane. Just as we were able to define a length constant, we can also define a time constant. Instead of how far, we have how long. The time constant is how long it takes a piece of membrane to charge up to 63% of its final value in response to a step change in its input voltage. Say we have an axon with a membrane initially at 0 millivolts, with a length constant of 1 millimeter and a time constant of 2 seconds. If we abruptly change the membrane voltage to around 100 millivolts at point A, what is the voltage at point B, 1 millimeter away from A, 2 seconds after we make the change?